Hey everybody, I wanted to take a little bit of time and talk to you about colligative properties today, and today's colligative property of choice is freezing point depression. Yay! I feel like when I talk about freezing point depression, I have to be overly excited. Anyways, that's neither here nor there. Let's talk a little bit about this. So, freezing point depression is what happens to the freezing point when you add a solute to a solvent. Okay, and so no matter what we do, because of the properties of the solution, the freezing point is always going to go down. So what we're talking about is the lowering of the freezing point. That's what we mean by depression, is that the freezing point is going to decrease when we add solute to a solvent. And it's dependent on the number of things that are present in the solution. And so if you have something like sugar, which when dissolves only has one thing that dissolves there. Okay, sugar's a non-ionic molecule, so when it dissolves, you just end up with one molecule. That's going to have less effect on something like sodium chloride, less effect than something like sodium chloride, which has two ions. It's an ionic compound, and so it will definitely affect water at least more. So, having PowerPoint issues here. Regardless, the formula for freezing point depression is very similar to the formula for boiling point elevation. The only difference here is that you have the freezing point depression constant. And for something like this, I think that there's a really neat real-world application when we're talking about the Van't Hoff factor. The Van't Hoff factor is that thing that I was talking about just a few seconds ago, where sugar, when it dissolves, because it's a covalently bound molecule, you only end up having one molecule floating around in solution when it dissolves, as opposed to sodium chloride. That's a soluble soluble ionic compound, which when it dissolves gives you Na plus and Cl minus. And so you have 2, so the Van't Hoff factor for sodium chloride is 2. So that's going to definitely affect the freezing point more than something with a Van't Hoff factor of 3. But now let's talk a little bit about salting the roads. Here in New Jersey, we have roads that get icy, and we need to prepare the roads in the wintertime by salting them, or even after it snows, we'll salt the roads. But we don't use sodium chloride for a myriad reasons. One of the chemical reasons we don't is that the Van't Hoff factor is 2. What we can do is we can use calcium chloride, which when it dissolves gives off 3 ions, because you have a calcium and then you have 2 chlorides. You have Cl minus and Cl minus. So this has a Van't Hoff factor of 3 as opposed to 2. So it really can affect the freezing point depression better than sodium chloride. Now, just a quick note on the Van't Hoff factor here is that you want to make sure, I just want to say that the Van't Hoff factor isn't necessarily exactly equal to the number of ions, but for what we use this in chemistry for, I think that gives you a close enough approximation and tells you kind of exactly what goes into determining the freezing point depression. So, let's do a sample problem here. Okay, and so this sample problem is asking us to list the solutions in order of increasing melting point. So the one that has the greatest, so it's going to go with the greatest freezing point depression up to the one that has the least freezing point depression. Okay, so there are two things that go into the freezing point depression. Okay, there's the constant, of course, but that's always constant. There's the molality, and there's the Van't Hoff factor. So what's the Van't Hoff factor of this, of sugar? Sugar is a covalently bound molecule, so the Van't Hoff factor for this is 1, and the molality is 0.1. Now for sodium chloride, the molality is 0.1, but the Van't Hoff factor is 2. So of these two, which one's going to have the greater freezing point depression? Okay, well, this is going to have the greater of the two, this guy right here. Okay, so now this has a molality of 0.08, but its Van't Hoff factor is 3. So now we're getting into some kind of tough comparisons. So what I'm going to do is, because this is really just then we're going to multiply by the constant, I'm just going to take these two values and I'm going to multiply them. So 0.1 times 1, this is 0.1. 0.1 times the Van't Hoff factor here is 0.2. 0.08 times 3, because that's the Van't Hoff factor, so that's 0.24. And then here we have a molality of 0.04. And what's the Van't Hoff factor for sodium sulfate? That's going to be around 3 as well. So here this is 0.12. Now, we want to do increasing melting point, so we want to know which one is going to have the largest freezing point depression first, because we want this is always going to be the change, so we want the greatest change in freezing point first. So this is going to go, and I'll do this in red here, this is going to go 1 at the top, and then 2, and then 3, and then 4. Okay, so that's a sample problem where we're kind of applying the ideas of freezing point depression. Okay. Now let's do another sample problem, but in this case now we have the freezing point depression. We want to know how much ethylene glycol, that's antifreeze, we're going to add to the water in order to lower its freezing point from 0 to -10. So delta, whoops, helps if I, let's just erase it all here. Okay. Or not. So we know that delta freezing point is equal to K FP times molality times the Van't Hoff factor. Okay, so we have the change in freezing point. The change in freezing point is -10.0 degrees C. The freezing point constant for water, I'm looking it up, you'd have to be given that sort of thing, is -1.86 times the molality, which we don't have. That's what we're going to end up solving for in this case, because we want to know the mass. Van't Hoff factor doesn't have mass. The constant doesn't have mass, and temperatures definitely don't have mass. So the thing that we're going to be solving for is this guy right here that I completely butchered when I drew it, but that's what we're going to be solving for. Okay, so I'll write it in red. And then times the Van't Hoff factor, and this is a completely covalent molecule here. This is all hydrogens, oxygens, and carbons. So the Van't Hoff factor for this compound is going to be 1. So now we can do some math. Let me call up my calculator. Okay, so when we call up the calculator here, we go -10.0 divided by -1.86 helps if I turn it on. Negative 10.0 divided by negative 1.86. Okay. And then divide that by 1. So what we know is our molality has to equal 5.376 must equal the molality. Now remember, molality is moles of solute per kilograms solvent. Well, this, once we get moles of solute, that will allow us to get to mass. Get to moles. Moles is very important. If you haven't heard me say it, you will soon enough, saying how important moles is. Okay, so now, do we have kilograms of solvent? Sure do. So this is going to be equal to 5.50 over the number of moles of, I'm just going to abbreviate this EG. Okay, so we now have that times 5.50. So the number of moles of ethylene glycol we need is 29.57 moles. Ethylene glycol is equal to 29.57 moles. Now that's not quite the mass. We have to use the molar mass. And so we know that for every 1 mole ethylene glycol, okay, I should probably move the calculator so you can see that formula there. Okay, maybe over here. Okay, so we have 6 times 1 for H, right? 1, 3, 5, 6. We have 2 times, and then we're going to go plus 2 times 16 for O, plus 2 times 12 for carbon. So that's 62 grams. And so now we can take 62 grams times 29.57, and we get 1,833 grams of ethylene glycol to lower the freezing point of water by 10 degrees. So again, this is another sample problem where we're trying to show how freezing point depression is used in the real world. Okay, everybody, have a great day and see you soon.